what are the kind of problem I'm going to look at? Okay, so I'm going to talk first about generative modeling. It's going to be the motivation for the talk. And we will see that eventually we'll solve a problem that is actually quite distinct from generative modeling and is closer to the so-called of transfer learning in machine learning. Okay, so I'm not sure. I mean, this is Monte Carlo crowd. I'm sure some of you are familiar with this type of material. Others might not be. So I'm going to have a kind of brief review of generative modeling, and in particular of the kind of most popular class of generative models which are currently available, which is the class of denoising diffusion models. Okay. So generative modeling, there's no kind of a pretty very clean definition of it. Is literally I give you samples, you have access to n samples from some distribution pi, okay? So kind of data distribution. And the aim of the game is to generate new samples which are approximately distributed from pi, okay? So really, so I think of it in the course of this talk, the sample I'm going to get are, say, images, okay? And I have access to a database of images, and I want to generate new images that looks like the one in the database, but are not carbon copy of the one currently available, okay? So that's a kind of really generative modeling. So it's not like Monte Carlo. Pi is not known up to a normalizing constant. I only have access to n sample from it. Okay, so that's a really different setup from the standard Monte Carlo setup. So this is a huge, like, very important problem in machine learning, and there's been a wide range of methods that have been developed over the years. So until 2018-19, the kind of like prominent class of techniques for generative model was the class of generative adversarial networks, but essentially it got superseded by the class of denoising diffusion model, which is the one on which I'm going to focus during this talk. Okay. So it's extremely popular in the literature. So really, the number of papers on the topic is really ridiculous. I mean, it's going up exponentially for the time being. And you can think that any kind of like, type of data to which this thing could be applied, it's been done basically. It's been done for protein, for video, for anything you can think of. So I give you here some examples. So this is, if you look at, say, Delhi-free, ImageGen, Runaway, these are all these kind of popular application to generate images. This is based on diffusion. There's basically, you can do 3D image generation with that. For video, there's like Veo that has been developed by Google, and there's also Sora, and many of basically diffusion model have been used to generate such videos. And also it has been successfully applied to the generation of protein, actually. Okay, so this is really ubiquitous class of models whenever you want to do generative modeling. Okay, so how does it work, this class of models? Okay, so like here, what I'm doing is like nothing new, is just a review of existing work, where essentially what you do is that, okay, you have access to some samples, I say n data samples. And what you're doing is like essentially you're going to progressively noise those samples according to a very simple noising mechanism that I will describe mathematically a little bit later. Okay, but essentially what you're doing is just like corrupting progressively your image, so that essentially if you run this corrupting process long enough, you have essentially Gaussian noise sample. Okay, and at the distribution level, what you've been doing by applying this noising process is that you are starting from a really complex, typically high-dimensional multimodal distribution, and by adding this noise, essentially you Gaussianize the distribution. So here, this is a simple example in one dimension, where you start from an original data distribution that is on the real line and is bimodal, and you follow this noisy mechanism. And if you look at what happens at the population level, this bimodal distribution becomes some kind of like, Gaussian distribution. Okay. So that's basically the original idea. So you have data sample, you noise basically it, so that this complex data distribution becomes a Gaussian distribution. On generative modeling, what it does the reverse. So essentially, you're going to inverse this kind of mechanism. okay? Literally at the sample level, it said that starting from Gaussian noise level, you're gonna build the kind of inverse of this noisy mechanism, that is a denoising mechanism that's gonna allow you to generate some actually data sample, at least, sample approximately distributed according to the data distribution. Again, at the population level, is really you start from the Gaussian distribution, and essentially progressively you're going to get back to the data distribution. Okay, so that's the key idea. So now obviously the question is, how do you do this mathematically? Okay, so I didn't want to spend all the talk talking about denoising diffusion model, because essentially this is not the main topic of the talk. It's just a necessary introduction for the material I'm going to present. So it's going to be a bit brief, but because you're all doing Monte Carlo methods, you all are familiar with SD, and in particular this kind of Langevin dynamics. So it should be easy for anyone attending this talk to follow the details. Okay, so we're going to formalize this noising on denoising mechanism in the following slide. Okay, so how are we doing that? So noising, so I'm going to think of everything in continuous time. Obviously, in practice, when you're having, obviously, it's run on your computer, you have to discretize process, but let's forget about that for the time being. The presentation is actually much more intuitive, I think, or more elegant when you do things in continuous time. Okay, so what really the noising mechanism does is say, what it does is you pick a sample, X naught, from your data distribution, Q naught. I'm going to call Q naught the data distribution. I have access to N sample from it. And what you're doing is literally you run an Arnaud-Lenbeck process, basically, over time. Okay? So this is really a simple thing you're doing. Obviously, the Arnaud-Lenbeck process is nothing but a Langevin dynamic that targets multivariate Gaussian. Okay? So what you do, what this transformation does, is that at the population level, the distribution of xt as t increase is going to basically converge to a Gaussian distribution. Okay, so that's the kind of literally very simple noising mechanism. So you start from the data distribution, you just apply essentially your noise from this kind of Arnaud-Lenbeck process, and after time t long enough, essentially you have actually a Gaussian noise sample. Okay, so you can think of it as this kind of like SD as transporting the data distribution Q naught to essentially the Gaussian distribution, okay, Qt, if you run it long enough. And we see here that this is not a complicated Monte Carlo, I'm using Langevin if you want to run this noising thing, but I'm using Langevin to sample from a Gaussian. So that's actually a very simple problem, actually. I'm not using it to sample from a very complicated distribution. It's just a simple, Arnaud-Lenbeck. Okay, so that's the simple noising mechanism. What about what is the kind of reverse? What is this denoising mechanism? Well, you have to think that really it's just simply the time reversal of this forward diffusion. Okay, so really what I want to do, if I want to denoise, what I'd like to be able is to simulate really the process that corresponds to the time reversal of this forward noising dynamic. Okay, so that's really what is key here. Okay, so what is this time reversal? Well, it turns out that the time reversal of a diffusion, it's also a diffusion process, but obviously with a drift that is modified. And what happens here is that when you write the time reversal, you have a drift where you have a component which is simple because it's just linear in the state, but you have also this component that appear, and this component is what is called Stein score. So this is essentially the logarithmic derivative of Qt. And what are those Qt terms? This is the marginal distribution. Qt is the marginal distribution of xt under the forward dynamic. Okay, so when you want to do this time reversal, you have this quantity that appear. Okay, so that's actually the kind of be the tricky bit, because obviously because Q naught was a very complicated distribution, Qt, which is essentially a noise version of Q naught, is typically unavailable. So we're going to need to estimate if you want to run this kind of like, time reverse dynamics, this denoising diffusion, we're gonna have to estimate this quantity, okay, which is the score, actually. Okay, but if we could do this, if we could run this diffusion, well, essentially it would be done because we would initialize it at the final time marginal q capital qt. So this thing is the marginal distribution of xt, x capital T under the forward dynamic is roughly Gaussian. So I could approximate that by a Gaussian noise sample. I would run this diffusion forward. And I know that at time capital T, I would have basically a sample from the data distribution. So that's the key idea. It's just a simple time reversal. Okay. So as I say, this is a very nice, neat idea, conceptual idea. And the credit should go, actually, I didn't mention it, to Sascha Sol-Dickstein, who's a former colleague at Google. And he was revisited essentially by, in particular, Yang Song during his PhD at Stanford. Okay. So the problem is that if you want to implement this time reversal to do generative modeling, you need to estimate the score. Okay, so I said the score is intractable. So what are we going to do? Well, we're going to make obviously some approximation. So basically keep in mind that really the process we would like to be able to simulate is this process. Okay, it's not accessible. So this is the ideal denoising diffusion I would like to run so as to basically generate new samples. It's not, you cannot run it. So what you do, you're going to approximate the intractable quantity, okay, by some, essentially, some neural net approximation. Okay, so it could be anything, but typically people use a neural net, and the architecture of the neural net does have impact on the performance of the procedure. Okay, essentially you replace, also initialize it as a Gaussian noise sample, which is a very reasonable approximation because we know that essentially Q capital T is roughly Gaussian. Okay, so this is what we like to do. We like essentially just simply approximate my diffusion I just approximate the initialization of the denoising diffusion by a Gaussian and replace the score by a parametric approximation. But obviously the question is, how do you actually come up with a good approximation of the score? Because it's just unknown, okay? So what we do is very simple. We say, okay, this thing, think of it as basically a stochastic process that induces a path measure, which I denote capital P. This one is another diffusion that basically induces another path measure that I denote Q theta. And we're going to learn simply theta, the parameter of the neural net that I'm going to basically use to approximate the score by minimizing the Kullback-Leibler divergence between P and Q theta with respect to theta. Okay. So if you do that, you can see by a very simple application, essentially, of elementary, stochastic calculus result, that essentially this is equivalent to minimize this loss here. So this is minimizing some kind of integral over T of the expectation under the forward dynamic, the forward diffusion, which is trivial to simulate, of the square difference between my parametric approximation of the score and the true score. Okay. So that's a kind of obvious loss you would have come up with, even if you knew no stochastic calculus. But it's obviously useless because you don't have access to the score. So, I mean, you cannot really minimize this loss function. But by a simple kind of trick known as the kind of denoising score matching trick in the literature, you can rewrite this loss. Minimizing this loss is equivalent to minimize this loss, okay? Where I've replaced here the intractable score by the gradient of the log transition under the forward dynamic. And because the forward dynamic is a simple Einstein-Riemann-Beck process, the conditional distribution of xt given x naught is a simple, essentially, Gaussian distribution, which I can I can compute the parameters of it exactly. Okay, so essentially, when you want to learn the score for your intractable score, what you can do is simply minimize this loss. Okay, this is given by intractable expectation on integral, but you can use simply some kind of stochastic gradient so as to solve this problem. And it's a pure regression problem. It's very, very simple. So this is where, there's some benefit of this method compared to generative adversarial network, because there's no adversarial problem, which are very typically unstable numerically. Here, simple regression loss. Okay, so that's what people do. So one thing which will be good to keep in mind is that really when we are doing that, what the score corresponds to get perhaps a better idea what the score, what does this quantity corresponds to, well, you can see simply that the score for the simple forward dynamic that I use is a very simple Einstein-Langback process, is simply something that is proportional to the conditional expectation of X naught, the clean state, the clean data, if you want, given the corrupted version of it. Okay. So really, what you're doing, so when you're running this denoising diffusion, is that you're basically going into the direction of expectation of X naught given Xt. So really toward the actually what you believe is the clean data. And if you run this diffusion till time capital T, you have actually a sample of the true data distribution. Obviously, we have approximation because we don't know the true score, but that's the kind of idea behind those techniques. So it's actually very neat, very, very neat, actually. Okay, so that's nice. And this thing is really at the core of all the application I presented to you before. This application to do image generation, video generation, protein generation. Okay, so that's what people have been pushing. So obviously, the huge literature on what are the best parameters, the best forward diffusion, kind of like ways to get better loss and so on and so forth. But, this is really the core idea behind denoising diffusion. Okay. Now, I'd like to extend this type of ideas to a little bit more general setting. So essentially, what we've been doing so far is that really we have this denoising, this noising diffusion that takes us originally from data distribution to Gaussian distribution. So this build a transport from data distribution to Gaussian on really generative modeling. It's a kind of algorithm, the denoising diffusion, that transport the Gaussian distribution to the data distribution. Okay, but in a sense, it seems quite restrictive because somehow the transport we build with those diffusion is only between Gaussian distribution and data distribution. Okay. And you might want to use this kind of same idea to build transport map between any two empirical distribution living on the same space. Okay. So that's one thing you might be interested in. And people in machine learning, it turns out, are very interested in this type of generalization. And I'll present some example later on. Okay. Also, so it seems the denoising diffusion model, so they build some kind of transport map, but is it any close to the optimal transport map? Is there a benefit of having like an optimal transport map, in this context? Or is it just having a regular transport map is just enough? We'll see. We're going to discuss those points later in the slides. Okay, so what I'm going to present now is essentially trying a generalization of those ideas to essentially building a transport between any two distribution living on the same space. Okay, so what are the type of application we're having in mind? So this is something that in the machine learning literature is often referred as unpaired data translation. Okay, so I think I'm going to pick an example, which is not an example that is treated, but maybe give you a better idea what's going on. So typically, say you want to do translation between, say, French and English, then you would have access to a lot of pair data that is a French text on its English translation. And based on those pair data, you would learn a mapping that takes you from French to English. Okay, so that's the kind of pair data translation. But you could consider the scenario where instead you have a bunch of French text, a bunch of English text, and you never have access to any translation. And really, you would like to build, just based on those two actually data set, build a kind of transport map that would take you from French to English. Okay, that seems a little bit crazy, but essentially on in text, people have tried that and it's not very successful. But for images, for example, it has been proven quite successful. So an application we will discuss later on in the talk is an application to climate science, where people have access to some kind of low resolution, essentially simulation of some kind of geophysical fluids dynamics. I mean, I don't know exactly the detail on really, and you have access to high resolution also, but those data you have access, they are not paired actually. Okay, and this is not the way. You don't know the mechanism that would take you from high resolution to low resolution either, because this is not something that just consists of subsampling. Okay, this is much more complicated mechanism. So the question is, just based on this kind of low resolution simulation, on high resolution simulation, can you come up, with an algorithm that just only require you to do the low resolution simulation and build a transformer that take you to high resolution simulation? Okay, so another application is perhaps something you've already seen in some paper, where people give you, they have access to, I don't know, image that correspond to summer, okay, and you want to take them to actually, produce the same image, but basically, during the kind of winter season. So you want to have an algorithm which automatically take your image that was, taken during the summer, and it just basically generate an image that looks like it had been basically, taken over the winter. Okay, so this is the type of application. So there's like things that are really funny between zebra and horse, for example, or to automatically convert this kind of like, a video of zebra, automatically it become a video of horse, for example, this kind of thing. So this is something, this is like big business in machine learning. So there's a very famous paper that was based on generative adversarial network that was published in 2017. There's almost already 25,000 citations, and people really care about that. Obviously, because it's based on adversarial network, it's actually quite unstable to train. And obviously, we think, well, if you can do it with adversarial network, there must be a way to do it with diffusion. Okay, this kind of diffusion idea. And this is what we're going to present today. Okay. So just going back, we're going to say, okay, currently, remember what we've done? We have like basically this kind of diffusion model that take data distribution to some kind of Gaussian, okay? And the reverse correspond to your generative model, okay? But now how do we do if we want to generate two, a transport map between any two distribution, living in the same space, okay? So it turns out, also, do we need diffusion at all? I mean, really? Is there really need for stochasticity? Couldn't we do anything with OD? So there's a whole literature on that has appeared over the past 2 years, basically. I will review some of it, and I will present some extension we've come up with over the recently, actually. Okay. So start with basically this method that has become extremely popular over the past 2 years, which is known as flow matching. Okay, so this flow matching is a method that gives you, if you have sample from two distribution, pi naught, pi 1, is going to be your transparent map that take you from pi naught to pi 1. Okay, so how does it work? So what you're going to do, you're going to create essentially, you're going to embed the problem in continuous time. Okay, and you're going to create somehow a path of intermediate distribution by considering simply a linear interpolation between x0 and x1. Okay, so if you pick me your sample from pi naught, sample from pi 1, and I'm going to call pi t the distribution which is obtained essentially by mixing, considering 1 minus t x0 plus t x1. Okay, I can do that. Okay, so that this thing, because that t is basically an index that takes continuous value in 0, 1, that creates, if you want to think as a kind of path measure. Okay, so here I give you an example that is taken from the paper from Kyung Liu. So this is the distribution pi naught here. Okay, the distribution pi 1 is a simple translated version of pi naught, and I give you essentially some paths that are generated by the simple linear interpolation. So if you pick pi naught here, x naught here, on x1 here, you're going to have a path here. Similarly, you got x naught that has been taken from this, bottom left, and you go to x1 for the top right, and this is another path it generates, and so on and so forth. Okay. So that's basically, we build like that, this kind of interpolating sequence between pi naught and pi 1. Okay. Now I'm saying I want to transport, my goal is to transport, essentially come up with a way to transport my sample from pi naught to sample from pi 1. Okay, so what I'm going to do, I'm going to say, okay, I can rewrite xt by just rewriting this simple expression. Xt is simply x naught plus t, x1 minus x naught. Okay, that's obvious. Just rewriting of this very simple expression. So in particular, I can write the following ODE that tells you the derivative of xt respect to t is simply x1 minus x naught, which you can rewrite again as x1 minus xt over 1 minus t. Okay? So this ODE is by construction an ODE such that xt follows the distribution pi t if x naught is from pi naught and x1 is from pi 1. Okay, but you notice this is not a standard ODE because this is the ODE which needs to know, the final point x1, so that your drift is dependent on future x1. Okay, so you need to define x1 first, okay, and then basically run your ODE. This kind of thing is completely useless from a generative modeling point of view, actually, because really you want something that just takes, if you were in a generative modeling context, pi naught would be the Gaussian distribution, pi 1 the data distribution, and you want something that is only based on the sample of x naught, just basically would build an ODE that would take you to the data distribution pi 1. You don't want to have something where you need also already to sample, a data point from pi 1. It can be completely useless. So this transport ODE, yeah, sure, what I've written is trivial, but it's actually useless from a generative modeling point of view, okay? Or for any transport type point of view. Okay, so what's the magic? Well, the magic is the following thing, okay? It's called known as Markovian projection sometime in the literature, which is that if you look at the ODE I had before, so what was appearing in it, you had x1 minus x naught, which you could rewrite as well as x1 minus xt over 1 minus t, okay? And I say it was useless because it depends, this ODE somehow from a for generative modeling, because it depends on this x1, which is unknown, actually, okay? So I'm telling you that now, if you replace the drift, this drift that depends on the future here, you replace it by the conditional expectation given xt equal x. So this is now your new drift for your ODE at time t, okay? Then obviously, because it's a conditional expectation, this thing doesn't depend on the future anymore. And it turns out that this ODE, basically, this drift, basically, if you plug that in your ODE and you initialize your ODE at pi naught, you have basically the sample of xt, which are still marginally distributed according to pi t. Okay, so that's quite magic, actually, because literally, by just literally solving having to compute this conditional expectation, which in the case, again, of a generative model where pi 1 would be the data distribution, on pi naught would be Gaussian noise. This thing is simply a denoiser. So this is exactly like denoising diffusion model presenting before. You can see that just basically solving this problem, estimating this conditional expectation, you come up with a transport map. Okay, so that's quite nice. Because again, this conditional expectation, you can solve it by a very simple regression problem. You can learn an approximation by a very simple regression problem. So that's actually quite magic, actually. So very, very simple method. I should say that this idea, actually, a Markovian projection, first appeared in this literature, actually in the unpublished work by Stefano Pelluchetti in 2021. And actually, it should be mentioned on this slide because he should really be given credit for having introduced this idea to the field. Okay, so let's look at what we are doing when we are doing this. So remember that basically, before, initially, what I was telling you is that basically, you had sample from pi naught, sample from pi 1. You were basically picking, to build pi t, you were picking pair of sample from pi naught, pi 1 at random and doing a linear interpolation between your sample. And I was inducing this kind of literally path actually measure. Okay? So this on the path in particular can cross. Now, if you're using this kind, so you assume that you have like basically done this, or now you use this path so as to construct an approximation of a conditional expectation of x1 given xt, but this can be obtained by just solving a very simple regression problem. Then, if you plug that, now you have in your ODE, with this new drift, then it creates a new basically path. What you know is that marginally xt is always discrete according to pi t, but now because your paths are generated by an ODE, in particular, there's no crossing anymore. Okay, that's quite nice. Okay, so that's good, but is it good enough? Okay, so you could ask myself, well, okay, I would say, sure, it's good. You've built a transport map that takes you from pi naught to pi 1, okay? It's actually, it can be run, and people have been using flow matching quite successfully over the past 2 years. There's a lot of application of it because it's so simple to implement, actually. Okay, now it remains a little bit disturbing in the sense that really, remember this is pi naught here, and this is pi 1. And if you really want to move sample from pi naught to pi 1, it seems that, having half of the mass here, like in this mode that goes down and then further up to get back to this, this part of the pi 1 distribution, it doesn't seem very optimal, okay? You could say, it doesn't matter, I don't care about optimality if I only care about transport. Well, the problem you see is that it has numerical implication because obviously, numerically, you have this OD that takes you from pi naught to pi 1, but you're going to have to discretize it, okay? If basically the trajectory of the OD are quite, curves, the curvature of those trajectories is quite high, then obviously you're going to need more step. Whereas, if ideally just that straight line, then it would be very, very simple to discretize. Okay, so that's why, wouldn't it be nice if you could do something where basically I could, the path I would create, the trajectories of the OD I would have to generate were actually straighter. Okay? Well, we know that we could do that. One way to do this would be essentially to solve a optimal transport for some kind of L2 cost. So I'm just going to get through that. So we're going to say now, okay, this thing is good. This flow matching is nice. And it's very simple to implement. But maybe we can do better by essentially having this generating actually flow which are actually straighter. Okay. So that's what we're going to do. Okay, so we're going to revisit that. Now we're going to say, okay, what I want to do is instead of just trying to come up with any transport map between the distribution pi naught and pi 1, I would like to find one, okay, that minimize essentially the expected costs, okay, between. So I'm going to consider all the joint distribution which has a marginal pi naught on pi 1. And I'm interested in finding the joint distribution which minimize this expected cost. And the cost here in my case is simply basically, the square Euclidean norm. Okay, so, and I know really from theory that if I could solve this problem, there's a dynamic formulation of it. I'm not going to have time to describe it right now, but basically, essentially, I would have essentially an OD with tracked paths. So that would be great. So the problem is the optimal transport thing. It's difficult to solve. It's unstable, expensive to compute. So we're going to come up with some kind of relaxation. So what we're going to say, okay, I'm not going to try to solve this problem. I'm going to try to solve this kind of so-called entropic optimal transport, which is literally, instead of solving the original optimal transport problem, I have basically this kind of entropic relaxation. So if epsilon is large, well, it's going to favor coupling between, that is pi is such that this coupling is just that, essentially it factorizes between pi naught and pi 1 if epsilon was large enough. But if epsilon is small, you get closer to the optimal transport. Okay? So this entropic optimal transport, formulation, this kind of relaxation of optimal transport, has a lot of nice mathematical properties and has been really actually popularized in machine learning by my colleague Marco Cuturi, where he used it. There's a kind of algorithm known as SynCorn to solve this kind of problem. But it turns out for the application I'm dealing with, those algorithms don't scale. Okay, so we have to come up with something different. Okay, so we're interested in solving this problem, essentially, because we say, well, if we could solve that, really, we would have actually transport map that have essentially good properties. Okay, but how is that related to these diffusion things I've been talking about? It seems like now I've completely dropped, this kind of continuous time formulation that was appearing in the denoising diffusion model on inflow matching. So now it's not there anymore. Well, it turned out that you can make it repair. So I would like now to get back to some kind of diffusion framework. Okay. I'm going to say, well, okay, I'm going to solve a problem that is equivalent. I tell you, if you want to solve this entropy, regularized optimal transport problem, that is finding the joint distribution that has pi naught essentially on pi 1 as a marginal and minimize this cost, okay, then what I can do is solve the solving problem. So I embed everything back to continuous time. And I'm going to say, I want to find basically the path measure, the diffusion that basically induce the path measure P that minimize the Kullback-Leibler discrepancy with basically the path measure induced by the Brownian motion, subject to basically this path measure being such that at time 0, you have pi naught as first marginal, and at time 1, you have pi 1 as second marginal. Okay? So the point is that it's actually equivalent. So if you solve this problem, you can you manage to find this path measure that minimize this Kullback-Leibler discrepancy on path space, and you just ignore what's happening, between the endpoint, then essentially the coupling, basically, the joint distribution at time 0 and time 1 of this optimal path measure correspond to the optimal coupling. Okay, so that's quite a nice result, and it's quite trivial to prove, actually, at least informally. Okay, so I'll give you an example here. So it's like you had two distribution pi naught on pi 1, and basically what I'm generating here is actually diffusion that induce the optimal path measure. So it's essentially induce the Schrödinger Bridge. Okay. So we managed to reformulate our kind of entropy-regularized optimal transport problem as some kind of, diffusion type problem. Okay, we still have to solve that. All right, so what do we know about the Schrödinger Bridge? So there's been a lot of work by very smart probabilists over the past 50 years on the Schrödinger Bridge. And in particular, they have characterized the Schrödinger Bridge. Okay, so you can show that the Schrödinger Bridge is the only essentially path measure which admit at time 0 pi naught as a marginal, at time 1 pi 1. That is Markov. So essentially, this path measure is induced by a Markov process, a diffusion in our scenario, and is reciprocal. Reciprocal, that means what? That means that conditional upon the endpoint, the conditional distribution is a Brownian bridge. Okay? So the only path measure that has these four properties is the Schrödinger bridge. Okay? So what could we do to learn this Schrödinger bridge? The standard algorithm is known as iterative proportional fitting, which I'm not going to discuss because it turns out that it leads to numerical algorithms which are not as good as the one I'm going to present today. But this is the one that have been favored in the literature for many years, and in particular, the SynCorn algorithm can be thought as a simple instance of iterative proportional fitting. So now here we're going to work on an algorithm we call iterative Markovian fitting. So that was proposed in a paper last year with Yu Yang-shi, Andrew Campbell, and Valentin. And this algorithm works as follows. So you're going to start from a measure, which is like a path measure, which you have at marginal at marginal at time 0 pi naught, at time 1 pi 1. Okay, you're going to do some kind of, instead of going a straight line and in flow matching, you're going to have like some kind of actually Brownian bridge. Okay, so it's kind of perturbation of it. Essentially, what you're going to do, this thing, it's a kind of non-Markovian, if you want, path measure. It's induced by a non-Markovian process. And you're going to do some kind of Markov. You're going to come up with a Markov process that has exactly the same marginal. Okay, so it's very similar to what they're doing in flow matching, where you have like literally the deterministic process, which is not induced essentially by some kind of causal process, and you come up with some kind of ODE that has exactly the same marginal distribution. So we're going to do exactly the same. Okay. Literally, once we've obtained this new process that has exactly the same marginal as the one as the previous one, it induces a new coupling between the time 0 and 1, and we're going to do what we call a reciprocal projection. On this reciprocal projections, just say, well, just forget about what happened between the endpoint and replace everything by a Brownian bridge and iterate, just redo Markov approximation on reciprocal and so on and so forth. So for those of you who know well the literature, this thing is nothing but some kind of stochastic version of rectified flow. Okay? So how does it work in practice? So this is pi naught here. This is pi 1. So you start by basically essentially building some path measure. Instead of drawing straight line, you draw Brownian bridge between the points, the pair of points between pi naught and pi 1. Okay? So this thing is nothing but the equation of the Brownian bridge, okay, which obviously depend on the point x1 because it's a bridge. And what you come up with an SD that has exactly the same marginal. And the way you come up with this SD is by simply replacing x1 by the conditional expectation of x1 given xt, which you can learn for regression. So again, it's just very, very similar to flow matching. Okay, but except not having ODE, we have SD. Now that define, a new path measure, okay, new process, and in particular, even if you had started with point x0, x0 and x1, which are independent originally in the, for those original construction, now you've induced some dependency, you've coupled them, okay? In the next step, what you're doing is very simple. I say you just forget about anything that happens between the endpoint. You have introduced the dependency between x0 and x1. You replace, you delete what has happened in between those endpoints, and you replace everything by some kind of Brownian bridge. Not some kind, some exactly Brownian bridge. And you iterate. If you iterate this process, on assuming you could compute exactly this conditional expectation, there's always going to be some error. Then you converge toward basically the Schrödinger bridge, which is quite nice. Okay, so that's our result. Okay, so we use that for some kind of super resolution task. So this is those climate science data we were dealing with. Okay, so I remember we have access to data set. We have high on low resolution climate simulation, but the data are not paired. Okay, so on the aim of the game is to learn a mapping that takes you directly from low resolution to high resolution. And we see that those kind of techniques actually perform out of the box significantly better than at the time what were available in the literature. So here, this is a kind of like original essentially data point you have. You run your SD that corresponds to your Schrödinger bridge, and basically it's going to generate finally some kind of sample from high resolution image. Okay, so that's nice, but those algorithms turned out that people kind of don't really like them, and the reason they don't like them is because it's too costly. So why is it too costly? Is because, remember what I was telling you. So you have you iterate Markovian projection, reciprocal projection, Markovian projection again, and so on and so forth. Okay. The problem is that each time you need to do this Markovian projection, you need to learn this kind of conditional expectation, and it's expensive. Essentially, it requires retraining some kind of, it's as costly as retraining a diffusion model, really, at each iteration. And people don't like that. Okay, so that people are, it's not something that fits well with the available code base. So, most people just actually never do this kind of iteration because it's just not really very practical. So the question we're asking is, well, could we do something that doesn't require having this kind of like one iteration I train a diffusion model, and then again another one and another one? It's just too costly. Okay, so we came up with this idea, so Schrödinger Bridge flow. All credit to the original idea is to Valentin de Bortoli and not to me. The idea is the following: you say, okay, think at a path measure. Okay, so you're going to consider a flow of path measure that is defined essentially by this expression. Okay, so minus the derivative with respect to time of we call p hat is p hat minus this operator. So what is this operator? This operator, it takes the path measure, it do a Markovian projection, and then a reciprocal projection. Okay. And you can show that, well, the only fixed point of this flow, so that basically this quantity 0 is actually the Schrödinger bridge. Okay. So the question obviously, how are we going to implement that in practice, because the flow of path measure is non-trivial, obviously. So you're going to come up with algorithm to implement this kind of ideas. Okay. So we just simply discretizing time. Okay, and we end up with some kind of algorithm that looks like that. So you have now discrete time, algorithm. Should be a PN here. There's a typo. And literally, what you do, you're basically considering at time n+1, you're going to have some kind of mixture between your previous approximation of Schrödinger Bridge on this quantity. Okay, and for alpha equal 1, you recover the standard iterative Markovian fitting. Okay, so that's the kind of idea. Okay, so that's nice, but again, that doesn't tell you, or if you were just trying to implement that directly, it's not clear how you would have an algorithm that avoid having to do this retraining, of having several iterations at each iteration, having to essentially learn this regression function, which is as costly as actually training a diffusion model. So what we do is say, okay, actually you can rethink of this kind of algorithm as some kind of like a functional gradient descent. Okay, and really the loss function we're considering is this kind of correspond to the Markovian projection. So this is the thing. So assuming I give you, have like a joint distribution of the endpoint, okay, and this thing is the conditional distribution that is given by, which is basically correspond to the Brownian bridge. And essentially, what you're trying to minimize the square loss, essentially trying to solve the regression problem, actually, that is necessary when you're doing it, essentially this kind of Markovian projection. Okay, so it turns out that you can think of what we're doing as just really this algorithm I just had written before. It can be written equivalently as essentially having a process, which is a diffusion process with drift VT, on what you're doing is that you're updating it through some kind of non-parametric update. So the kind of functional gradient descent loss. Okay, so there's some detail here. I spare you, but this is the kind of idea. So really, we've replaced the problem of this kind of iterative algorithm, which is kind of a bit painful to implement, and we just say, well, it's equivalent to kind of solving some kind of like, doing functional gradient descent. Okay, functional gradient descent, there's no magic, obviously, because in practice, you cannot consider all the class of drift functions. So what we're doing in practice, obviously, we're going to parameterize the drift by some finite dimensional parameter theta, and we have some kind of parametric update instead. Okay, so this is what we are doing. Okay. Spare you the detail. I think I'm running out of time, but important bit is that this algorithm can be thought as follow. Okay, so you start, which is like by just doing what people are doing in flow matching on the so-called bridge matching. That is, you sample from pi naught, you sample from pi 1, you interpolate with some kind of, Brownian bridge. And if you put the volatility of the Brownian bridge to 0, it's a straight line. And then you do some kind of Markovian projection to learn an SD that takes you from pi naught to pi 1. This SD, this solution, is not the Schrödinger bridge usually. There's no reason that you would find the Schrödinger bridge in one step. So what you're doing then is basically you're doing some kind of fine-tuning of this original, essentially, transport map by minimizing the loss I was presenting before, on minimizing this loss, on generating new sample from the corresponding diffusion. Okay, so you have like an iterative algorithm to do that. On what we show under basically regularity condition is that this thing can converge to the Schrödinger bridge. So this thing doesn't provide a better solution than the previous algorithm had presented. It's just more convenient algorithmically because it just bypass having to essentially, doing this one training, repeated training of diffusion model. Okay, so I spare you the detail. So just to wrap up in the last 5 minutes, so this kind of diffusion model have basically, been ubiquitous in machine learning now. They just use everywhere for generative modeling. And what is nice is that this kind of ideas can be extended to compute transport map. Okay, and by tweaking them a bit further, essentially, you can actually approximate a solution to the Schrödinger bridge with some kind of entropy-regularized version of optimal transport. Okay. One thing which is not great about the techniques we've developed, okay, is that those methods, as what they call in the literature, is not simulation-free. So what does it mean that simulation-free? It means that basically, we train we learn the drift of the SDE, okay, and then we need to simulate sample from this SDE, so I have to kind of fine-tune the model, which is costly. Okay, so that's actually something which numerically, computation is actually very expensive. Techniques that try to bypass this problem, try to propose, solve the transport problem or the entropy-regularized version of the transport using this kind of mini-batch optimal transport of thin-corn. Those techniques basically don't scale well for, the large data set we're dealing with, actually. So they provide a very crude approximation of, what the transport is. This literature is a goldmine for problems because so many problems are really unsolved. So there are convergence results in the literature. People are catching up, but there's still a lot of open question, essentially understanding really why those methods works. For the pure generative model aspect, people have, very recently has come up with really interesting results, which partly explain already why those methods appears to work so well. But in the context of transport, there's barely anything. So there's a lot of work to do. So, the last point, which is, I think, relevant to this seminar, is that, it'd be good, you'd like to be able to kind of implement this type of ideas for Monte Carlo sampling, okay? Where instead of having, sample from 2 empirical measures, you would have, say, a Gaussian distribution and, say, a target distribution, which is defined up to a normalizing constant. It's possible to come up with some algorithm to do that, but they don't enjoy actually very good properties. For those of you who are actually quite familiar with variational literature, they're all gonna reverse with this kind, like rely on some kind of, you know, reverse scale criterion, or you subject to mode dropping and so on. So Monte Carlo, you know, it remains, it's, I mean, I'm sure there are a lot of things to do in this area using this type of idea, but it still remains actually completely unsolved. Okay, that's all. Thank you. I would like to put an acknowledgement. So this is my quotas.